on there, we're on over there. Yay, all right. Right, finally, welcome everybody. Thank you for coming. Thank you for braving the inclement weather. Apologies for the delayed starts. 2 cancelled trains on the way here before one finally turned up. This is what happens in Britain when we get like 2 flakes of snow. So, yes, oh well. We're here now, and we're going to be talking about the STL containers and algorithms again. We're now on session 6 of this module. So, is there anybody who's here for the first time tonight? 2 of you. Well, welcome. First of all, as you can see, as I just said, we're on session 6 of our module. So, if you if you feel a bit sort of overwhelmed tonight, if this is all a bit sort of, well, what's going on? Don't worry. All our previous videos, all the sessions we've done before, they're all on YouTube. This is being live streamed to YouTube now, and the recording will be available afterwards. So just go to our YouTube channel, youtube.com/CPP London Uni, and you'll find everything there, and you'll be able to catch up. There'll be no problem. Again, for the new people, because everyone else has seen this hundreds of times now, we have a Slack channel that we encourage you to join, so we can talk to you can talk to each other, etc. So we can give you news like where we're going to be next week, that sort of thing. So if you head to that URL, cpplang.now.sh, you just pop your email address in there, it'll send you an invitation to come and join the sort of roughly 2,000 people that are on the Slack. And once you join that, you'll be able to find our little chat room, which is #CPP London Uni. Okay, so last week we had a sort of continuation of the week before. So we were finished going over most of, not all of, but most of the standard library containers, at least the common ones that you will use, most likely use in your programs. This week we're going to go on to talk about algorithmic complexity. This is something that I was going to talk about last week, we didn't have time for. It's not really essential to know about, but it is helpful. It's a little bit mathsy, so if that's not your thing, don't worry about it too much. You can sort of tune out for a little while. But you know, do try and follow along. It's not too complicated.
Are you referring to data annotation?
Yes, exactly what I'm referring to.
Is it fun?
Is it fun?
Yes.
Well, I think it's fun, but I might not be the best judge of that. Also, yes, you're a long way away at the back, so if you can't hear me, then yeah, sort of wave your hand or whatever. And if, of course, as always, if you've got any questions, then just raise your hand or shout out or let me know. So yes, we're going to talk about algorithmic complexity, and then we're going to go on to talk about some of the how standard algorithms work, basically. And you've got a fun little exercise involving implementing some of those. Okay, so last week I left you with an exercise, which was this exercise to do with practicing using containers. So we did exercise 1 in class. Oh, I think most people did. Who finished exercise 1? About half of you. Who finished exercise 2? Oh, mostly the same hands. Excellent. So, those people who didn't finish it, would you like me to go over the solutions now, or do you just want to power on and do some new stuff? Power on. Okay. Well, if you are interested in the solutions, you can go to this URL. There are 2 branches. There's EX1 solution and EX2 solution. So the solutions for both the exercises are there. Basically, the second exercise was a matter of choosing an appropriate container in which to store the access codes. And in my opinion, the appropriate container was standard set, because you wanted to store a set of unique access codes and you wanted to add them and delete them. So set was a good choice there. You could have done it various other ways, but my choice was set.
What, to set the codes as active?
It's a standard set, the data structure.
Okay. Well, instead of
a vector. Yes, in this case. Okay, so any questions about the homework from last week? From those people who did it? No? Fairly straightforward? Excellent. Right, let's move on then. Let's talk about algorithmic complexity. So apart from the one person who's already chatted it out, what do I mean when I talk about complexity of algorithms?
How long it takes something to solve or something to resolve.
You have to say that a little bit louder.
So how long it takes something to resolve.
How long it takes to operate. Not a bad definition. I would go a little more general and say it's the amount of resources we need to execute that code, to execute that algorithm. And as John said, most of the time we're interested in how long it takes, the time, like the CPU resources. Sometimes we're worried about what they call space complexity, that is the amount of memory it uses. It's generally less of an issue these days, but still relevant for some problems. So, a word of warning for anybody in the room who has, studied computer science and knows this stuff inside out. This is really like a basic introduction, right? I'm not a computer scientist myself, and I've picked this stuff up, but I'm not an expert. So, if I've got things wrong, please correct me. This is really complicated. There are textbooks written on this. People do PhDs in this. So I'm only touching on the very basics today. And yes, if you can, there are hundreds of textbooks on the market. If you find this stuff fascinating and you want to know more, you can easily do so. Okay, who has heard of this thing called big O notation? A few hands go up. So most of the time, when we're executing algorithms, like say a sort algorithm, we're interested in how the performance changes as our problem size grows. So if an algorithm takes a certain amount of time to operate on 100 elements, how long does it take to operate on 200? How long does it take to operate on 1,000 or 10,000 or 1,000,000? And we have this notion called big O notation that's used to express this. And very roughly speaking, if we have a mathematical function, f of n, its behavior as n increases is dominated by the fastest growing term. This is not really a computer science thing, it's a maths thing. But as n tends to infinity, the behavior of this function is dominated by the fastest growing term. And that's called the order of the function. We write that as O of x. Sorry. Yes.
Call this order of the function.
Yes, big O.
As in, this is the biggest factor affecting them.
Exactly that, yes. So I'll give you an example of what I mean by that. So if we have an algorithm and we sit down and we work it out with pen and paper, exactly how many operations this takes, CPU operations. And people do this, and for simplicity's sake, we imagine that all CPU instructions take the same amount of time to execute. And so we've got our algorithm, and on n elements, it takes 4n squared plus 3n plus 8 operations, CPU operations. Then if we do it on just 2 elements, we're going to get 4 times 4 times 16 plus 12 plus 8, which is 36 operations. But if we do it on 10,000 elements, we're going to get 10,000 squared, which is 100 million or a billion, times 4, plus 3 times 10,000 plus 8. Well, when we've got a billion, 30,000 doesn't really, it's pocket change. If we operate on 100,000, well, then we're going to get 4 times 100,000 squared, which is, going to have lots and lots of digits, more than I can work out in my head. And then the extra 300,008 we get is, doesn't matter. We don't care. So as n grows large, as n grows very large, we say that the behavior of this mathematical function is dominated by the n squared term. So the n squared term here is the fastest growing term. And so in computer science terms, we say that such an algorithm, such a function that has this many operations, we say it has order n squared. It's an n squared algorithm. We write that as O brackets n squared. Again, if all this sort of maths is taking you back to school, high school, and you're a bit like, whoa, don't worry about it too much. This is more for information, so useful information rather than anything you actually absolutely have to know, right? So sometimes we get algorithms for which the runtime doesn't depend on how many elements we're operating on. Right, so I said to you last week or the week before, when we're looking at a vector, finding the element at position 10,000 in a vector, a very large vector, takes the same amount of time as finding the element in position 20,000. Right? It doesn't depend on how many elements we've got in the vector. As opposed to a string, as opposed to a list, sorry. For a standard list, trying to find the 20,000th element is going to take twice as long as finding the 10,000th element. Yeah?
Isn't that the same with an array?
Yes, a vector, yes. Vector is an array for these purposes. So if an algorithm we write doesn't depend on how many elements, we say it operates in constant time. Constant time doesn't mean 0 time. It still has to do some work. But it doesn't depend on how many things we're operating on. So it's a constant time algorithm. We write that as O of 1. But if the algorithm depends linearly on the number of elements we've got, that is, it takes twice as long to operate on 20,000 elements as it does to operate on 10,000 elements. If it varies linearly with how many elements we're operating on, we say that that operates in linear time, order n. So these are good. Constant time is the best we can possibly have in terms of algorithmic complexity. Constant time operations, brilliant, we love them. Linear time, well, that's not bad. For some algorithms, it's optimal. If you think about something like a find operation, right, that has to operate in linear time. Or count operation, because we have to visit every element to count them all, right? So there's no other way it can operate. But for some operations, order n is really not very good. So finding the nth element of a string, a list, sorry. We don't want that. That's a slow operation. We'd rather it was constant time, like a vector. Yes.
Is it worth just mentioning that the ON is the worst possible time it takes to operate, especially when you say you're finding something, because of course once you found it, you have to go to the...
Yes, yes. So yeah, I think I do mention this somewhere, but in general we talk about worst case. You're ordering the worst case. Now for most algorithms that's the same, worst case and average case and best case. For more really complicated algorithms like sort operations, these things can vary. So yeah.
I'm not going against what you said, but I know in things like quick sort, they have it's n log n.
Yes.
Thing, but the worst case is n squared.
That's correct.
And this is reversed.
Yes.
So best case, or the general case would be n log. It's not always the worst case, is it?
No, so in quicksort's a good example because quicksort, for those who don't know, is a very, very famous sorting algorithm invented by a guy called Tony Hoare. And it's very clever how it works. And it has average case n log n complexity. That is, in general, it operates, or the runtime grows with n times the logarithm of n, where n is the number of elements. But in the worst case, if you've got particularly nasty inputs, particularly crafted inputs, then quicksort can operate in n squared time, quadratic time, which is vastly slower, right? And it's for that reason, actually, that almost all sort of real-world sorting algorithms now use a sort of clever hybrid sort that if it detects that it's got this worst case, it switches to a different algorithm. So that's exactly what standard sort does, for example. So we have constant time, we have linear time. An algorithm operates in O log n, we call that logarithmic time. That's better than linear time. Log of n is smaller than n for any n greater than 1. N squared, I've already mentioned it. Quadratic time. In general, you want to avoid quadratic time algorithms. They're slow. But for some problems, quadratic time is the best you can do. If you can write a quadratic time matrix multiplication, you will make millions. You'll be very famous. For higher powers of n, we call that operating in polynomial time. This is obviously worse, even worse than quadratic time. We can also have algorithms that operate in exponential time, which is when things get really, really bad. You really don't want to try running an exponential time algorithm on a problem with any more than a handful of elements. So Ollie shared a graph that was very similar to this last week, but I found this on Wikipedia. And it's very good, and it shows you really what all these different complexity classes mean. So if you can sort of take this in, you don't really have to worry too much about the maths behind it. But if you can sort of take in what these mean. Then at the bottom, the best, the purple one, we have an algorithm that operates in constant time. And you can see that number doesn't vary as we increase the number of elements. The next one up, the darker blue one, is an algorithm that runs in logarithmic time. So it grows, but as we go on and grow our number of elements, it's just creeping up. Right, so this is not going to take significantly longer to operate on 1,000 elements than it does on 100. Right, we're approaching the limit, if you're mathematically minded. Root n, I don't know of any algorithms that operate on the order root n, but you can see that, again, that grows pretty slowly. So if we had an algorithm that had that time complexity, we'd be pretty happy. For linear time, it's just a straight line. If we double the number of elements, we're going to get some linear factor of that extra time taken to operate our algorithm. And then beyond that, things start to grow pretty quickly. So the yellow line is n log n. So that is n multiplied by something, so it has to be worse. It has to be above it on the graph. And it's multiplied by this factor, log n. Log n grows slowly. So yeah, it's worse, but it's not that much worse. It's a steeper gradient, but it doesn't grow steeper as we go up. N squared just kind of shoots up. If you think about You know, you can just work out some squares in your head and work out that they grow really pretty quickly. But not anywhere near as fast as exponential time, 2 to the n. Ghost opera. Ghost making coffee.
That's working exponential.
Sorry?
It's working exponential.
Oh, we could be here for a while. So exponential time algorithm is really, really, really slow. And finally, we have this factorial thing. Again, I don't know of any algorithms that would operate on factorial time, but I probably wouldn't try running them, even if I did. So these are, you know, some common. Well, a couple of them aren't very common, but these are gives you an idea of how of what these complexity classes need. How our runtime can be expected to grow as we increase the problem size. But big O is not everything. So if you go and you look up, you know, if you're that way inclined and you go and look up the research paper that describes the algorithm, it will invariably go into detail about its complexity. Big O isn't everything. It's important. It's very important in choosing an appropriate algorithm. But big O is only relevant to the largest growing term. It's only relevant as things get really big. If we're operating on a small data set, then other things become, the smaller terms can become important. So, for example, that example I put up earlier, what was it, 4n squared plus 8n plus something? When we've only got a few elements, that 8n term actually has some bearing. If we've got 10,000 elements, we don't care. But if we've only got 3 or 4, well, that would make a difference if it was 8n or 3n or 50,000n. So for small problems, small data sizes, big O is not everything. And in particular, modern computers have enormous CPU caches, and these can have very interesting effects. Because if you've got good cache locality, then at least up to a point you can overcome an algorithmic, a worse algorithm. Right? And a particular example I happen to be working on this week is that quicksort is no n log n average case sorting algorithm. And there's another kind of sort called insertion sort, which is n squared. So worse. You don't want to use an insertion sort. That's going to take forever. But if you've got a very small number of elements, if you've only got 10 or 20 elements, it turns out insertion sort has really nice cache properties. And insertion sort, even though it's an n squared algorithm, actually runs faster than quicksort for small problems. So when in doubt, measure. This is the golden rule that anyone will tell you about anything related to computer performance. Right? Don't guess. Measure. Run benchmarks. Test your code. See what it actually really does.
How do you measure?
How do you measure? Well, the easiest way is to just measure the time before you run your algorithm, measure the time after it finishes, and then print out the difference.
Yeah, but do you use like chrono, or do you grab like a stopwatch, you know, and just...
It really depends. If all your program does is just run the program, then you could use like the Unix time command. I've used that in the past. If you want to get a bit more complicated, you could use part of the standard library. It's called standard chrono, deals with time. And there's something called the high performance clock, and you measure the clock at the start, you measure the clock at the end, and then you print out.
Apparently that one is not very good.
High performance clock.
Yes.
It's high precision clock. Yeah. It's an alias for one of the other ones.
Yeah. So they said use either this or that.
Steady clock or
yeah.
system clock. Yeah. high precision clock is guaranteed to be the highest precision clock available. So I'd say use it.
If you want to time a very tight piece of code, then and if it's not running for very long, you use like built-in CPU performance counters for it. They're designed for that. Usually, though, people tend to just run something in a loop a million times and see how many seconds it takes to extrapolate from there.
And if you want to get really fancy, there's a very good and heavily used library called Google Benchmark. No prizes for guessing who wrote it. And that's the gold standard. If you're really want to heavily optimize your code, go with Google Benchmark.
Does it depend as well if you're doing the caching and the CPU optimization, depending on what hardware you're using, what operating system you're using?
The CPU caching won't generally be affected by that. That's sort of a product of just how much level 1, level 2, level 3 cache your CPU has. In terms of optimizations, yes, some compilers optimize some things better than others. That's again something you just have to experiment with, and it can be the case that you do something and it makes your algorithm run very much faster on one compiler, and then you try it with another compiler, and you find out you slowed down your code by 10 times. Yes, that's a tricky one. When that happens. So finally, this is supposed to be a module about talking about the STL. I've been nattering on about algorithmic complexity. So for operations on containers and for the algorithms, the standard CPU C++ standard doesn't actually mention how implementers are supposed to do these things. Right? It doesn't tell you to use one particular sort algorithm. What it does do is it says this operation has to operate with this time complexity. So standard sort, for example, is mandated it must operate in n log n worst case time, which means that actually you can't, according to the C++ standard, you can't use quicksort to implement standard sort. You have to do something a bit more clever. Stable sort is another one that has to operate in n log n worst case time. Nth element, all of these really complicated algorithms, time-consuming algorithms. In fact, all of them, in fact, are the C++ standard just says what time complexity they must have. So vectors, member access operator, square brackets operator must operate in constant time. You're not allowed to write an implementation vector that very slowly counts its way through every element. It's not allowed. You're not allowed to write an implementation of standard sort that has worse than n log n complexity. So, that was a little diversion into something a little more theoretical. Was that familiar to people, or is this new? New? Yeah?
I've heard of it, but not yet. So, just a question based on this last slide. When you say C+ standard generally,
Yes.
so does that mean what? That if someone's implementing an algorithm, they must ensure that meets
Yes.
this standard?
That means if somebody is writing, the people who wrote the C++ standard library
Yes.
have to abide by these rules, basically.
Right.
So
But then how do you measure that this kind of this function applies to this algorithm?
that this complexity, how do you do it? Well, the sort of long-winded way would be to gradually grow your problem size, make a note of the times, and then perhaps plot them on a graph, or do some sort of regression to work out. Fortunately, Google Benchmark can actually do that for you automatically. It's really rather clever. Works out the complexity of your problem if you give it the right options.
Or mathematically prove it
Or yes. And then if you're writing a published paper for a computer science journal, you'd probably be expected to mathematically prove your complexity. Yeah.
So is Google Benchmark just a library?
Download, yes. Yeah, you have to. It's a pretty big library. You have to compile it and link your program to it. But yes, it's freely available, all open source. So yeah. So, any questions about algorithmic complexity? Not really hard computer science questions because I might not be able to answer. But any more general questions about anything we just talked about? Yeah.
How often do you write code in your work that you have to think about algorithmic complexity? Is it like everyday occurrence?
It really, really depends on the nature of your work, right? If you're writing like, I don't know, just like some GUI software, like front end for something, you probably don't care that much, because maybe you're only going to be, you're only going to be sorting like a list of 20 email addresses or something. You don't really care. You want it to be fast, obviously, but yeah. For other problems, it really, really matters. So I used to work in the oil industry, and we work on just mind-bogglingly huge data sets, right? And you just cannot do complex operations when you're talking about data sets, petabytes in size. It's impossible, right? So you have to select your algorithms very carefully. You really want to try and avoid anything worse than linear time in that. Right. So it really, really depends on the nature of what you're doing.
Operating at scale.
Yes, exactly. Yeah. Any more before we move on? I'll have a drink. Excellent. Either I've sent everyone to sleep with the maths, or I explained it really well. So I'm going to choose to believe I explained it really well. Let's talk about the standard algorithms. Come on. There we are. So the standard library, C++ standard library, has lots and lots and lots of algorithms you can use to build your programs. Over 90 of them at the last count. And most of these are defined in a standard library header called algorithm, logically enough. Some, quite illogically, are in a separate header called numeric. This is a historical thing, and it's silly, and it shouldn't be the case, but it is. In particular, one that's very useful and is in numeric is something called standard accumulate. It does a left fold if you're a functional programmer. It's called standard accumulate, and it lives in numeric. And there are a couple of other algorithms that live in numeric. There's one called standard iota, which gets used a bit as well. So we've got 90 algorithms to play with. And they range from the really simple ones that you could pretty much do yourself with a for loop, like standard counts, and ones that you really, really wouldn't want to write yourself. Things like standard sort, standard stable sort, nth elements, in-place merge, really like quite complicated ones. Ones where you have to go and look up the papers for how to actually implement them. You don't want to do that, and luckily someone's done it for you. So my general advice to you is to use the standard algorithms whenever you can. Right, the people who wrote the standard libraries are pretty good at C++. Right? They're probably going to have got this right, and they're probably going to have made sure they get really, really good performance.
I like the Gregory famous quote, love other people's code.
Love other people's code, yeah, absolutely. Every line of code you don't have to write yourself is a line of code you don't have to debug yourself, usually. If other people's code doesn't have bugs, but you can be fairly confident that the standard library doesn't have bugs because it's used by millions of people. And when there are problems, they get found out pretty quickly.
Yelp was bug-free for a couple of seconds.
Sorry?
Yelp was bug-free for a couple of seconds.
It deleted itself.
Oh, right.
What's yeah?
Yelp's in the like restaurants.
Yes.
Is there any reference for people who are not familiar with the 90 algorithms that you recommend? So if I have something I want to do, I can check against.
Yes, there is. So there are a couple of good ones online. There's cppreference.com, which is like kind of the Bible for C++ programmers, but it's pretty dry and pretty hardcore and uses a lot of technical language. There's another website which is cplus.com, that is cplus.com.
That's good.
It's not quite as sort of dry and technical, it's a bit more approachable on C++.
And has examples.
And I think CPP reference has examples
But
as well.
they're much harder to understand.
Oh, okay. So my general advice to you is to use the standard library algorithms whenever you can. And you can sort of take this a bit further in little letters, because some people really hate this advice, but I actually think this is a good thing. If you find yourself writing a sort of non-trivial for loop more than perhaps, I don't know, 4 or 5 lines, you know, something, decent chunk of code in a loop. Take a little while and look at it and think about it and work out whether what you're actually doing is something that one of the standard library algorithms can do for you. And you'll find that in lots of cases what you're actually doing is a find, or it's a merge, or is a transform, or is a rotate. So there's a guy called Sean Parent who's pretty famous in C++ circles. He does a lot of talks, does a lot of good talks. And in particular, there's one very, very famous one that he did. It's called C++ seasoning. And he gave this talk at Microsoft, I think, about 2013, 14. And for me, this is probably the best C++ talk that I have ever watched. So it's available online. Go to YouTube, just, you know, type in C++ seasoning, it'll be there. And he really goes into detail. He takes this really complicated chunk of code from the Chrome browser, I think it was, and he goes through it and he shows how you can turn this into just a reasonably simple call to one of the standard library algorithms. Right, so I really recommend having a look at this talk just for a bit of inspiration, a bit of like, geez, that's good, right? Which is what I thought when I saw it.
Yeah, you know it's going to be a good talk. It starts off, as Lee says, like Google walk in to do their debugging.
So I've mentioned this lots of times already, but we had a little diversion talking about containers, so I'll go back to it. Standard library algorithms operate on ranges, on pairs of iterators that denote a range. And the first iterator of the pair denotes the starting element, the beginning of your range, and the second iterator of the pair denotes one past the last element that you want to operate on. Right? And actually, it's a couple of weeks ago when we were at Bloomberg, the gentleman who was hosting us, David, he gave me a really good explanation that I hadn't heard before as to why, when they invented the STL, why they went for this convention, right? So I'm going to have to do this backwards, so apologies if it doesn't work. But imagine you have 4 elements. How many positions have you got? 1, 2, 3, 4, 5 positions. Right? We can either be at the beginning of our range, there, and now we've reached the end. Right? So you can think of an iterator not as denoting an element, but to be denoting a position between elements. And when you dereference an iterator, it looks right. So we're at the beginning, we dereference our iterator, it looks right. This would be much easier with a whiteboard, but I don't have one. So you're just going to have to watch me waving my fingers in the air. So we begin here, we dereference the iterator, it looks right. We move our position to here. We dereference the iterator, it looks right. Move to here. Dereference looks right. Dereference looks right. We get to here. We're in the last position. Now there's nothing to our right. We can't look right, there's nothing there. And that's why dereferencing the end iterator is an error in your program. One that, if you're lucky, you'll get an error message, and if you're really unlucky, it will do horrible things like overwriting memory and, you know, be a horrible security hole in your program. Does that make more sense than when I was doing a sort of hand-wavy description of it a couple of weeks ago? I thought that was a brilliant explanation.
You see sometimes taking left-hand side and right-hand side chords.
That's mainly with like predicates, which we'll talk about in a minute. So yes, they operate on a pair of iterators which denote a range. The first element of the pair is the start of the range, and the last element in the pair is one past the end. It's a past the end iterator. And the reason they're written like this is so that we can easily operate on a whole vector or set or list or whatever container we have just by passing container.begin and .end. But it's also possible to operate on subsets of these containers. So you can just sort the first 10 elements of your vector, if that's a reasonable thing to do for your problem. Right? It's just as easy as sorting the whole vector. So let's have a little example. We've got this function, get some ints, returns a vector of integers. So then we can call this algorithm standard count. By the way, if this text is a bit small for you guys at the back, you do have another screen right there. So it's an algorithm called standard count. And what that does is it counts how many times this last guy appears in the R. Look at what I've done there. I'm sorry. Let me edit this slide. Come on. No. Would help if this wasn't like the slowest laptop in the world. Okay, the syntax highlighting's gone a bit mad. But now we have this variable called vec, which holds a vector of integers. So then we can call this algorithm standard counts. And we pass it an iterator to the beginning of our range, an iterator to one past the end of our range, and we want to count how many times the number 0 occurs in our list of integers, in our vector of integers. So it returns how many zeros it's found. and we can just print out their number. Here we're using another algorithm. This time we're using standard fill. And we're passing it the beginning of our vector, passing it the beginning of our vector. And there's a second argument. We're passing vec.begin plus 10. That is, begin at the beginning, find the position 10 places later, and we're passing begin and begin plus 10 to our algorithm. So the range, instead of operating on the whole vector this time, we're operating on the first 10 elements. Everything from between begin and begin plus 10. Before you do this, you have to make sure the vector has at least 10 things in it, otherwise you're reading past the end. You can imagine that code, isn't it? And what this does is it fills everything from the first position to the 10th position. It fills them all with the value 42.
Is there another way you could have like a safety check to ensure that, you know, that
Yes, you do assert vec.size greater than or equal to 10. Actually, if you use them,
could you use it like I don't know, like a lambda expression, so you have a more complex query?
not for standard fill, you have to give standard fill a value, but for many of the other algorithms, yes. And actually, just on the thing about if you overwrite the end, if you use the Microsoft compiler, or the Microsoft standard library, they use these things called debug iterators when you're not in optimized mode. They use these things called debug iterators. That will tell you, will quit your program and give you a message saying you overrode, you can't do this operation, basically. It will give you a warning. But that only operates, these debug iterators are very slow, and they only operate, they are switched off when you use optimized mode. But still, it's a pretty useful thing that Microsoft do. There are ways of doing it in other standard libraries, but I can't remember the right switches off the top of my head.
C-line doesn't have that,
C-line. It's not a matter of like what editor you use, which compiler you use. Strictly speaking, which standard library you use. So
I'd like to add something. Like
Use
you've
an
got
assertion.
the iterator library.
So,
Okay. You've got the iterator library, but you also have iterators built into other libraries. I hope I explained that well.
yes, so this thing about standard library iterators, we did talk about them quite a bit the beginning of this module. That was before Christmas, that was a long time ago now, right? The way the iterators are defined, iterators are like a sort of a concept. There's no one iterator type. So yes, there are lots of other C++ libraries that use this, this sort of iterator protocol. So they will provide iterators that you can use with the standard library algorithms.
So vectors have iterators, and then you have the iterator library.
Yes, yeah. So iterators are like the glue between containers and algorithms. Containers provide iterators, algorithms consume. Did you have a question?
Yes, that last line, Phil.
Yeah.
It starts at element 0 up to element 9. It fills in 42.
Yes. It fills the first 10 elements of the vector with the value 42. Except actually, I've just noticed it doesn't do that. It won't do that. Anyone tell me, I've made a mistake on this slide. Anyone tell me why this won't work?
Because like begin.
Oh. I don't know who said it, but someone gave me the right answer. Yes, I made a mistake. I declared my vector const at the top.
Alright.
So, does anybody know why? This is getting a bit more tricky. I have told you about it. Why precisely this isn't going to work?
Because you're not supposed to store stuff in constant variables.
immutable, you can't change it constantly.
Yeah, absolutely. So vec is, once we've created it, it's immutable, we can't change it.
It's been compiler probably allocates a set amount of memory because it's you defined it as a const. Once you've gone with that size of memory.
No, that's not the case because get some ints could, could depend on a runtime thing. Could be get some ints could ask the user to type in a load of ints, and the compiler can't possibly know how many the user's going to type. No, so what's going to happen here is that vec.begin is, because it's a const, because vector has been declared const, vec.begin is going to return a const iterator, a read-only iterator. And then later on, when we try and use standard fill, it's going to give us an error, something along the lines of, you can't assign through a const iterator. So yes, I'm actually going to edit that now so I don't forget. One slide with 4 lines of code and 2 mistakes on it. So this is going well, right?
The compiler should catch that.
Yes, absolutely will, yeah. Won't compile. So how are these things actually implemented? Well, they're implemented as what we call function templates. So I talked a little bit last week or the week before about class templates. C++ allows us to have what we call function templates as well. So a template is basically like a blueprint telling the compiler how to write this function. So a function template is not a function, it's like a blueprint for how to write a function. So when we make a call in our code to a function template, that is, we write its name and put the arguments in brackets like you call a function. We call a function template. What happens is behind the scenes, the compiler looks at our blueprint, it looks at the types we've given as arguments to our function, and it goes away and it stamps out a version of that template, a version of that blueprint, just for the argument types we've given it. And then the optimizer can see the types we're using. It has all the, yes?
It meant to avoid that we have to declare the return type up front.
Yeah, I'm not sure what you mean.
Usually you would have to declare a function with the return type in the declaration of the function.
Yes, that's also the case for function templates. In C++ 14, there's a facility that you can use auto as a return type. That means that it's deduced from the return statements in your function.
But what happens when we try to find similar functions but for different return type? If you already used auto before, then it's not available anymore for any other return type.
Well, because these are blueprints, right? So
you're talking about overloading.
Yes.
Return types are not part of the overload. You cannot declare 2 functions with the same argument.
What polymorph? I was talking about polymorphism. Sorry.
How is that related to polymorphism?
Let's say we have two functions that have the same name but different return types.
Yeah, that's overloading. That's not polymorphism.
Oh, okay.
But yeah, the return type is not part of the overload set. If you have 2 functions with the same arguments and different return types, just won't compile. You can't do it. They have to have different arguments to be a valid overload.
Decal types are the same types.
Sorry?
Decal type.
Decal type is used for saying I have some L value and I want to use this as the type of that thing. So if I have like a std vector called x, I can use decal type x, and it says, okay, what is x? Well, it's a std vector. Okay, that's the type.
yes, decal type gives you the declared type of a variable. And yes, you do sometimes see it used in return statements, particularly in C++14, in the form of decal type brackets auto, which is just also deduces the return type. It uses slightly different rules to the way auto does it. But anyway, yes. Function templates. When we call a function template, when we instantiate that template in the lingo, the compiler creates a version of that function from the blueprint just for our types. So if we call a function template with an int argument, and then we call it again with a float argument, we're going to get two versions of that function produced by the compiler. One for ints and one for floats. And perhaps, you know, somewhere else in our code we'll have a third version for strings. And this isn't in our code. This is generated by the compiler from the blueprint, but it exists in the machine code that the compiler generates. And this means that the optimizer inside the compiler sees these generated functions and it's and it sees exactly the types we're using. And it means that it can do all the optimizations that it can do because it knows exactly, it has all the information there that it can possibly have. Right, so this notion of templates in C++ is very similar, visually at least, to how generics work in Java and in C# and some other languages. But it's much, much more powerful, in part because the template language is actually Turing complete, which is, you know, kind of crazy, but also because of this thing of actually generating completely separate versions of functions, completely separate versions of classes. And it means we get all the optimizations we can possibly have. This is why, one of the reasons why C++ is a fast language that it is. It allows for unbeatable, almost unbeatable efficiency. So let's have a look at what an implementation would actually look like. So I'm going to go and have a look at standard count, because that's one of the simpler ones. I think starting off with standard sort might be a bit much, right? The text on this is going to be quite small, so you guys might want to turn around a bit. But yes, let's have a look at standard count. So this is an actual, like, proper implementation of this, by the way. This is not messing about. This is not simplifying it for educational purposes or anything. First of all, if you look at the second line, we're declaring a function called count. And it takes 3 arguments. The first 2 are of type iter. And the third argument, third parameter, has type reference to const t. And it returns standard size t, which is an alias for some integer type that's appropriate for holding sizes. Right. Size type, size t. So on the second line, it looks like we're declaring a function. But then just above that, we have this keyword template. And that tells the compiler that we're not declaring a function here, we're declaring a function template. We're writing a blueprint for how to produce the count function. And inside this, the names iter and t are going to refer to 2 types, which we can specify later. These are what are called our template parameters. So we look at the implementation. We initialize a counter with 0. Then we do something funky. This is a 3-element for loop, right? Not a range for loop, but an old school for loop with 3 arguments. And usually when we have the 3 arguments, the first one is our initialization step, the second one is our test condition, and the third one is the increment step. So in this case, we don't need to do any setup for our for loop. We don't need to initialize any variables or anything. They're already done. And we want to terminate when first equals last. So we're going through our vector or whatever container it might be. When we reach the last position, we terminate. So this is going to keep executing this loop as long as first is not equal to last.
So what would happen? It is possible if you go beyond last with such a notation.
In this case, no, because we're incrementing first by 1 step. If you were jumping first in 2s, you might have to be careful about it. But
so then it will just simply go out of range.
Well, you get bad things happening. So yes, we'll keep running this loop for as long as first is not equal to last. And then every time after we execute the loop, we're going to run this third bit of code, which is ++ first. That is moving the iterator forward 1 position. Then we have the body of our loop. If star first equals value, ++ counter. Okay, so what is this doing? Can anybody tell me?
It increments a counter every time you encounter a value of a given value.
Okay.
So it counts. The number
It counts, yeah. Which is appropriate for a function called count, right?
Yes.
Yeah. Specifically, can anybody tell me what the star first bit is doing?
Dereferencing.
Dereferencing, that's the word I was wanting to hear. Yes. It's dereferencing the iterator. It's obtaining the value of the thing at that position. So, look at this loop. We first initialize our counter to 0. We enter the loop. We dereference our iterator. We say, okay, what's the value of the thing at that position? If that's equal to our target value, the value we want to count, then we increment our counter. And we do that over and over again for every value in the container. Just working straight forward through the container from first to last. Then we return the counter and we're done. Something important to think about here. What happens if somebody gives me an empty range?
0. Counter will be 0. You won't even go to the for first equal last.
Exactly, very good, yes. If we have an empty range, or an empty range in C++, if we have an empty vector, for example, begin and end are equal to the same thing. Begin and end return the same thing for an empty vector. So now, if first and last are the same, we enter the loop, set the counter equal to 0, and we run the test of the for loop. It's immediately going to test, is first equal to last, or rather, is first not equal to last? And if that fails, because they are equal, the body of the loop is never incremented. So in that case, we never dereference first, which is good because it's equal to last. You don't want to do that. So this is safe for empty ranges. This is going to do the right thing for empty ranges. This is good. And this, by the way, is literally what your standard library count algorithm looks like. Cleaned up a little bit, but variable names wise.
They use assembly to do this, so it's faster.
No, you can.
So they use just this code,
Uses exactly this code. Yeah, you'll be able to look it up. Yeah.
Not that useful.
Sorry?
It's not that useful because you can write this yourself and it doesn't take much.
I think it is useful. I think it is useful to write,
It's boilerplate.
you know, number of threes in my vector is standard count thing 3, right? Because if I'm looking at the code in 6 months' time, if someone else is looking at the code, working out what it's doing, they can just go through and go, oh, you're counting the threes. They don't have to look at this for loop and go, what's this for loop doing?
But you can create your own count and just count.
It's what we call boilerplate code. You don't want to write.
I know what you're saying. It's a standard. They'll know how it works. And it saves you from typing, I guess.
Yeah.
But you'll only have to type it once anyway.
Just have this simple
They create function template as well. But if it's
Someone's already done that for you.
Yeah, exactly. If it's a standard, then they already know that it's like that. If they've used it, it's the standard.
Yeah, you had a question about it.
What is now the value add of implementing it as a template?
What's the value of implementing it as a template? Well, let's have a look. It's a good question. So let's have a look at calling this. So I'm going to create a vector of integers saying 1, 2, 3, 4, 1. Now I'm going to count the number of ones that occur in this. I'm going to pass ints.begin and ints.end. So what actually happens when I call this function? Well, the compiler's going to go and it's going to look at the types of the things I've given it. And it's going to do something called type substitution. So it's going to look at the type of its.begin, which is going to be, you know, standard vector, angle brackets, int, colon, colon, iterator. It's going to be some like private iterator type in the standard library. And it's going to substitute that wherever it sees iter in the original blueprint, in the template. And then it's going to look at the type of 1, and it's going to say, well, that's an int. So it's going to work out, well, it's going to deduce that t is int. So wherever it sees t, it's going to replace that with int. So what this is going to do, it's going to synthesize a function called count, especially for these iterator types and for ints. And it's going to know it's dealing with ints. And it's going to know it's dealing with vector iterators. And it's going to be able to see all the vector code, because that's a template as well. And it's going to be able to probably inline this dereference operation, so that's not going to be a function call. That's, well, pretty much the only thing it can do. No, it's going to be able to inline the iterator comparison there. Yes?
So this one I'm getting is here. So if you have right code, we've got 15 different types of vectors.
Yeah.
And we want to count them. We just use our boilerplate. We just use our template.
Yeah.
So we don't need to make a special. We don't need to do. We don't make a sort of count for ints. We don't need to make a count for this. We don't need to account for that.
That is absolutely precisely the point.
Yeah, so that's why it's right.
The type name means that you can use any.
Yeah, I understand. That's what I'm saying. I'm trying to say. So rather than saying, why would you write this? Because come on, everyone can write that. So I see the importance of trying to write that code, because I'm just going to go with this. I'm going to write this once. I'm not going to have to do it again for any of the
but if you write, you can learn from it. That's
no, what I'm saying. You're saying, why should you write the code?
This code
You
is
said,
the
you could write it. So
standard, because you can learn something by writing.
You absolutely can learn something by implementing some standard library algorithms.
no,
You might just be doing that in about 10 minutes' time. So
No, listen, I was trying to address your problem. You said, why would you write that?
Yeah.
You can do it yourself. I know how to write that. That's easy, everyone can do that. But I'm just trying to say from why I think you say, why would you write that? You just want to write it once, and it gives you every
just want to do
computation.
you're insane, you just want to write.
I'm never insane, I'm not insane.
No insane, no insane,
Not
no insane
Full
with algorithm. Insane as in, you want to do things yourself, you don't want to use the library. You just like doing the code yourself.
yes.
And if you learn from
What would have been the difference, like, if we would have declared it as a normal function and would have said as the types auto, keyword auto?
Well, you can't use auto as the parameter type for a function. That's not something you can't use. You couldn't say count brackets auto first.
You can't say instead of type name that you put auto there.
Instead of type name, you, in C++17, you can use the auto keyword there, but it does something slightly different. It doesn't declare. It would say. So
it's better for built-in types.
No, it does something quite different to type name. So type name says whenever you see iter in the template, that refers to a type. And if you use auto, that's saying whenever if you said like template angle brackets also I, that would be saying whenever you see I occur in the body of the template, that refers to a value of I.
Also, this for constant expressions like values.
Yes, yes.
And that's it. That's all.
In template parameters.
Yeah. If you use the 3 dots after auto, you can have like a list like that.
Yes, there are variable templates, but that's getting a bit further into this than we want to go right now.
Where would you define your templates? Would that be a separate header file?
Yes, so you have to put, or generally have to put template code in header files.
Okay.
Right, so, and the reason for that is if you wanted to call count on, a list iterator, which would work perfectly well, in order to actually generate this function, the compiler has to be able to see the source code of the function, right? Otherwise, how can it possibly go and generate it?
And the templates, they have like a portability issue here. So, like they have this problem with portability. So they suggest that you put like the definition and the declaration into header files.
Yes, you need to you in general need to put all of the whole code that is the
in header files.
Definition as well in header files. Yes. So yes, when we call this function, when we call count with int.begin, int.end, it's going to substitute int in place of t, and this horrible looking type, standard vector angle brackets, colon, iterator, it's going to substitute that wherever it sees iter. So it's going to create a specialized version of count just for our types. It's literally what they call it, what it's called, a specialization of count just for the types we give it. So now let's try it again. This time I've got a list of floats. And I can call our count algorithm on our list of floats. And this, again, this works perfectly well. We're using a different iterator type, and we're using a different value type. But still, our template works fine. And what's going to happen this time is the compiler is going to create another specialization of counts. With t equal to double, and iter equal to standard list of floats. Why did I do this particular example? Well, it's just to show you that t is deduced from the thing we give it, not from anything related to the iterator type. Right? So the iterator iterates over floats, we've given it a double, but we can compare floats and doubles perfectly happily, that's fine. So this call is going to work just fine. And the point is that we've created two different functions, function specializations from our template, from our blueprints. And those specializations can be optimized independently, and they will be heavily optimized for the types we've given. And this allows for really unbeatable efficiency. This makes things really, really fast. there's no such thing as a free lunch. There are downsides as well, but you know, we won't worry about those too much right now.
This
Yeah.
should be easy to implement in assembly, I think.
Probably not for lists, because that's a linked list, right? So you're going to have to do lots of pointer chasing. It won't be much fun. It's going to be considerably easier to do it for that. And then you get to things like standard maps and standard sets.
Maybe you can transfer it to an array or something. Or maybe in the end it doesn't turn out to be faster to do that.
What CPU you want to compile it for as well.
Sorry?
If you let the compiler compile this and you tell it what CPU you're going to put it on, it can generate less code for that CPU. If you're going to put it in assembly.
This is like standard, so doesn't the standard like use threads automatically for this? Doesn't it like create threads for this?
No,
it doesn't. What's good with threads now?
Because threads are a scarce resource, right? You want to.
But you might have like a long list of numbers that you want to find.
Yes, and actually in the standard library, C++17, there is a version of count that can use multiple threads if you wanted to. The basic version won't, but you can do it.
Well, it's an execution policy.
Yes. You can say...
You can create one yourself. Would it be difficult to create one with threads?
For this, not using OpenMP, that would be quite easy, I think. Yeah.
Or just different.
Yeah.
Depends if you know what you're doing.
Yeah.
Huh?
Depends if you know what you're doing.
Sorry, I think you had your hand up.
I was just wondering whether if you actually have two, if you call the function twice but with different types, whether the compiler really goes down to different branches when it sees what you feed the template with. And because you say you can really optimize it for the way that you use it.
Yes. So this is as if we had written a function count which takes two arguments of type standard vector iterator and an argument of type const reference to int, reference to const int. This first call is exactly the same as if we had written a version of the function, especially for those types. And the second version generates from the template a function that is identical to if we had, by ourselves, written a non-template that took standard list, angle brackets, float, iterator, and const double ref.
I understand that, but I just don't understand how it's different than for the compiler, because what he does in the end should be pretty much the same.
Choose a different data.
Yeah, because the way you increment an iterator is different for lists and for vectors, for example. So for a vector iterator, it's really, really simple. It's basically just like a simple index into an array. Right, so that's incrementing that iterator is really super fast operation. For a list, it's a slightly slow operation, because if you remember we were talking about linked lists, every node, every address in our linked list holds the address of the next node. So you have to go and ask the node, okay, where's the next place that I have to go to? It's the postman delivering letters all around the city, right? And then we have to go and we have to go and fetch that value from somewhere else in memory. So just the increment operation on these iterators is quite different. So for vectors, it's a very fast, very simple operation. It will almost certainly be inline. It will probably just be inline to a single assembly instruction. Right? The index will be held in a register and they'll just increment that, and it'll be super fast. For lists, it has to do something a bit more complicated. This algorithm will not operate as quickly on lists. It's just the nature of the beast. You cannot iterate through a list quickly, right?
Do you put templates inside classes?
You can put templates inside classes. Yeah, you can have template member functions. You can have class templates. You can have template member function templates.
Template inside the template. Template inside the template.
You can have member function templates of class templates. Yeah. There is, by the way, there is in the C++ standard. There's a limerick. There's a limerick that tells you about all the types of templates you can have.
Okay.
Or no, sorry, the limerick. There's a massive, complicated paragraph telling you all the types of templates you can have, and then afterwards, for anybody who's managed to read through that without their eyes starting to bleed, there's an Easter egg in the standard. It's limerick.
Because I was just thinking, Is it clever enough if you start putting class using your type names?
Yeah.
You can't start putting your own classes.
Absolutely.
You can.
Oh, absolutely. Yeah, so if you wrote your own data structure, if you wrote your own data structure that followed this iterator protocol, if you like, that gave iterators, then you could pass that to count, no problem.
Okay.
Any kind of container you like that follows this iterable, or this range protocol, like proper terminology.
So if your class wanted, say, your class wanted to deal with say, strings, vectors, or whatever, you could write a template for it in the mem function when you're defining the class.
Yes, or you might make that a class template. I don't know particularly what you have in mind.
Or if you have like a vector in a class, you can just pass the bar vector to count. You don't have to pass the class, because if you pass the class count, this count to standard count, it does not pass it. The vector inside your class. So you pass just a vector, that's in your class to count. It's the same thing.
Yes. Yeah.
It's still a vector. It's just in a class. So you do class name dot. The vector. Begin of the
Okay. So the point here is we get template specializations, we get that code optimized just for the types we use. Right. So the question was roughly like, why is that good? What advantage does it give? So for example, when we do this comparison, this if star first equals value, well, that's just going to be an integer comparison, which again is going to be a single CPU instruction. But when we do it for floats, we're going to be, we're actually going to be comparing two doubles in this case, and that's going to again optimize to just a couple of CPU instructions, different instructions to comparing ints though. So we get code that is specialized, literally called a specialization, specialized just for the types that we've given it. This is style of programming. It's weird and often not very easy to do, but it's generic programming. It's really a term that's coined by Alexander Stepnov, who originally wrote much of what is now the C++ standard library. He wrote the original STL. And he coined this term generic programming for doing things in this style, for writing a generic function like count here that can operate on multiple different data types and do so with maximal efficiency.
You're guaranteed, I mean, as long as you use the type, the templates and the standard library stuff, you're guaranteed to optimize your code. I guess.
Yes, I mean, subject to the usual, there are silly things you can do that inhibit the optimizer.
So to go over what you said, so by taking like count and putting it in a template, that's generic programming, because there's other ways you could do that.
There are other ways you could do it. So, for example,
I could have a for loop, and I could just use vector in and iterate through it, and then put like the beginning and end in count.
Then you could use it for separate strings. So you could use it for something like strings.
Yeah, I know. I said there's other ways I could do that.
oh, right. So you're saying about this iterator first and last. You're saying, why can't you just pass the vector?
No, I was saying that's the proper term for when you put it in a template.
Templates allow this sort of style of generic programming, right? Is that?
I think we're close in understanding. But yeah. You mentioned that the author said this is a style of programming, and that's what I wanted to clear up.
Yes.
Yeah,
So there are other languages in which you can do this generic programming style, right? So it's a style of programming. Like we talk about object-oriented programming or functional programming or any of these other sort of buzzwords. Generic programming is kind of one of those buzzwords that we talk about, a sort of style of writing code.
Yeah, generic programming means you can use like different data types. That's the generic programming. You can pass int now, you can pass float later.
So before you move
That's called generative programming, right? You can create like a function template that you can use on ints and then on floats.
Yeah.
So that's called generative programming. Right?
Yeah. It's the idea behind it, yes. Yeah.
So this is templates are part of it.
So that's the term for that kind of programming.
That's why when they in books when they talk about templates they say templates and generative programming because templates are part of generative programming.
Yeah.
Anyway, sorry. Yeah, just a quick note for anyone, because obviously it goes online. Maybe don't try comparing floats. It's usually a terrible thing to do because of imprecision. So you might run that one and not get what you expect.
Yeah, particularly as in this case, the float's going to be promoted to a double. I think 2.0 can be represented exactly, but in any case, this isn't necessary. The second one is not necessarily a great example of something you should do. However, it is valid code and it will create a version of the function specialized just for those types, which was really the idea of the demonstration.
There's a terminology for like a different way of programming.
Yeah.
If you weren't aware of it, you would be like, oh, well, I've just generic programmed.
No.
Okay,
no.
That's what I'm trying to get across.
Okay, yeah.
That's generic programming.
Yeah,
There's other ways of doing it. Okay.
Yeah. But it's, if you write a base class with virtual functions and then you override those virtual functions in the derived class, you might not know that you've just done object-oriented programming. But you've sort of, virtual functions in inheritance would allow object-oriented programming style to be used in C++. And templates would allow a generic programming style to be used in C++.
Because when I use that, I just say, well, I use the template.
Yeah. Yeah. I wouldn't get too hung up on terminology, right? You probably put 5 programmers in a room and they'd have different opinions on what these terms mean anyway. So.
At least 6 opinions of that.
Yeah. Okay. Let's go on to talk about predicates. Predicate, scary sounding word. Not a very scary concept. Many of the algorithms allow us to pass things called predicates, which dictate how they work. So what is a predicate? Well, it's just a function that returns a bool. It returns true or false. Well, I say a function. Actually, C++ is a bit more flexible. We're allowed to pass other things which we can call. So C++, you're allowed to have function objects that have a call operator. You can write lambda functions, which is effectively the compiler just writing a function object for you. These things, the sort of the catch-all term for them, we call them callables. So a predicate is a callable which returns a bool. This thing about function objects and lambdas, by the way, allows us to have stateful predicates, which is really useful. But for now, we won't worry about function objects and lambdas. We're just going to worry about regular old functions, functions we know. So a function returning a bool that we pass to a standard library algorithm, we call that a predicate. And specifically, we have unary predicates, which take one argument. And it may not surprise you to know we have binary predicates that take 2 arguments. So some algorithms require us to pass them unary predicates. Some algorithms optionally allow us to pass unary predicates that modify their behavior. Some algorithms require us to give them a binary predicate. Some algorithms, optionally, we can provide them with a binary predicate. So let's have a look at using predicates. Press space too quickly for my laptop. There we are. So I've got this struct person. I have a first name and a last name. Nice and simple, right? And then I've got a Boolean function called compare person. should be compare people, I don't know. Compare person takes two people and compares them. So, if these two persons, these two people have the same surname, same last name, well, we compare their first names alphabetically, lexicographically, technically, alphabetically, right? So if we have two people both called Smith, then Adam is going to come before Benjamin in this example. But if the last names are not the same, then we just compare the last names alphabetically. Right. So the idea of this function is that it tells you whether person A comes before person B in the alphabet. If you were to list everybody in the phone book, ordered by surname and then by first name. Right. If person A has a surname that is earlier in the alphabet than person B, this returns true. If they've got the same surname, it looks at the first names. So let's now create a vector of people. And we imagine we've got some code that fills it up with people. Now, we want to find the person who we should put first in our telephone book we're writing. We want to find the person whose name occurs first, Mr. Adam Aardvark. Right? How do we do that? Sorry, what I mean, I don't mean we specifically want to find that name. I mean, given the people, we want to find the person whose name is first, alphabetically. You could use a for loop.
So you need to find. You need to look through the vector, every name, and then you need to compare. When you get the first element, you compare it to the name that you want. Compare the name that you want with the name that you got from the vector, using that compare function until you find.
I think you're right. But when you're talking about the standard library algorithms,
what's the name of the operation?
Yes, at the back.
I think we were talking about how
How are you?
You could just sort your vector and take the first element.
You could, that would absolutely be one way to do it. You could sort the whole vector and then look at the element in the first position, in position 0. Absolutely you could. But if we've got a whole phone book of people, we've got...
Adam is in there, in the vector.
Oh, that was just a name I invented.
So it's supposed to be in there, because if you sort, then yeah, you can...
No, just forget about that. I shouldn't have mentioned it. I just want to find, given all these people, I want to find the person whose name is earliest in the alphabet. Right?
Then that is still enough vector for this person, yeah? So yeah, you use that vector. You sort it, and then you get the top one here.
Yes, absolutely. We could sort the vector. But we've got, maybe we're trying to compile a phone book and we've got thousands of names in it. Yes. Yeah.
Couldn't we just go, if you're looking for the smallest one, can you just say the first element's the biggest?
Yeah.
And then check the next one. If that's bigger than that, you swap around.
Yeah.
You always know where the smallest element is.
Yes.
Without sorting this.
Yeah. So sorting this is a lot more work than we actually need to do. We don't need to have the whole thing sorted. We just need to know the person who we put first in this example. So sorting, yes, that's a way you could do it, but it's doing more work than we need to. What we really want to do is to find the smallest, the least person
Use
according
find.
to this comparison.
Use the find. Just to define.
Almost. We want to find the minimum element in this vector.
Find it.
Find min. What? Just find min or something like that.
Almost, you're all so close. It's min element is what we want. So there's a function called min element. And min element has a version that takes 2 arguments, just the beginning and end of the range, and that will try to compare whatever you give it, just using the regular less than operator.
They've got something like similar in Java as well. We have to search something like that, like when using a sort function.
Yeah.
How you can use a comparable something, you have to implement something called comparable.
Yeah.
We have to define what your sort is like. Is it based on the first name? Is it based on the number?
Yeah.
So it's exactly the same.
It's exactly that. Yeah. So Java, I think, has like a comparator interface or something that you have to. Yeah. Yeah. So this is exactly the same motion. Yes.
Is the computer going to have to get instructed to assign a numerical value to an alpha value, so that A is less than B? So A is 0 and B is.
That's not quite how it works. No. No. Well, let me just go back to talking about min element. There's a version of min element that just takes 2 arguments and it goes through and it compares. Imagine we had a vector of ints. We want to find out what's the smallest int in there. We can use min elements and just pass it begin and end, and it will compare all the ints just using the less than operator. So we'll go through and it will say, okay, let's look at position 0. Maybe position 0 is 72. And okay, the lowest we've seen so far is 72.
Does it return a negative number if it's before?
For instance, it would, yes.
Yeah.
What's the order of the algorithm?
This is an order n. It has to be, because it has to go through and check the whole vector. So, for instance, this would go through and look at the first element, maybe the first element is 72. Then the second element, you look at the second element and say, see that's 42. And go, okay, so the lowest we've seen so far is 42. And then the next one, maybe the next one is -3. Okay, the lowest value I've seen so far is -3. The next one's 28. Is that lower than -3? No, it's not. So my lowest is still -3. And it would go through the whole vector, and that's the way it would find the lowest value. That's exactly how min element works. It doesn't have to sort the whole element. It's just an order n operation, just races through the data, constantly updating what's the lowest it's found so far. But that's for ints, using this less than operator. For our person struct, well, we don't have a less than operator, because there are multiple ways. Perhaps for other uses, you don't want to sort them surname first. Perhaps for other purposes, you want to sort them first name, last name. Right? So in this case, we can pass a comparator function, a predicate, pass a predicate to this min element function, a binary predicate.
Would you just use a not, like put them inside the parentheses and put a not at the estimate before the parentheses? And that basically means the opposite of.
That is not going to work for a function. No. So in this case, we're passing this predicate, and what it does is it goes through and it looks at the first element and says, okay, that's the lowest we've got so far. And then it compares this lowest we've seen so far, and it compares it with the person in position 2. And it runs this compare function with the lowest so far on the left, and the other one on the right that we're looking at. And it says, okay, is this new one lower than the one we've got? Well, if it is, we're going to save it and move on. So every time, rather than just using the less than operator, as it would do if we didn't have this last bit, it's going to use our predicate as the basis for comparison. So this allows us to customize how this function works. Allows us to sort of, it gets the minimum element, but it lets us define what we mean by minimum. Lets us define what we mean by something, one element being less than another. And we're using a predicate to do this. And yes, min element is a template. So we're going to get a version of this function that is specialized, not just for comparing people, but to comparing people using this predicate. And it means that it's going to be able to, as long as it can have the code for compare person, well, it will be able to see the code for compare person. It's going to be able to inline that code. And that's going to make it super fast.
It goes on implicitly, compare person is implicitly passing each element. In the implementation of min element, it will repeatedly call the function with 2 appropriate arguments. Does it pass to that function the end, the character past the end?
No.
Never that. So you can
No, because the people who wrote min element are
okay.
experts, and they know not to dereference the end iterators. Yeah.
So to build my own function that would allow me to dictate an operation that works with an element, I always have to have 2 arguments for the function.
For min elements requires a binary predicate. Right? Because if you think about it, it's here our compare person function is doing what the less than operator usually does. And less than takes 2 arguments, right? You do a less than b, return to bool.
I must always follow this logic that min element always suggests the first argument is less and the second argument is...
Yes, it returns true if the first argument is less than the other, and returns false otherwise. So yeah, that's actually quite a good question. What's going to happen if 2 persons have the same first name and last name? What's compare person going to return? 0. It's not going to return false. Yes, it's going to return false. Because if they have the same first name and last name, well, first of all, it's going to check the last names. Are they equal? Yes, they are. So it's going to say, is the first name less than the second name? Well, if 2 things are equal, then one is not less than the other. So this will return false.
Question Ben Wiles.
Yeah.
Feel free to bump this at the end or whatever. How does, when you call std min element, you're passing in 2 iterators and the predicate, right?
Yes.
So that we know that the people.begin and people.end are of
type vector iterator.
Std vector iterator.
Yeah.
How does std min element know that they're going to? How does the compiler get person from that vector, from that iterator, in order to determine whether it's being passed to the correct type?
Because from the iterator, actually it doesn't do any type checking. It tries to compile it, and if it works, then great. And if it doesn't, you get a spew of error messages. Right? But if you're writing a bit more of a clever implementation, what you could do is you could look at the type that star returns, operator star. You can use decl type to work out what star iter does. Right? Or even easier than that, you can just ask the iterator what its associated value type is. There are ways of doing this. I didn't want to get too deeply into it.
Right, yeah.
So yes, min elements finds an iterator to this smallest thing in the vector. And then, assuming that the vector is non-empty, it's going to give us a valid value, so we can go ahead and dereference that and find the person whose name occurs first. The person whose name occurs first alphabetically. Now the thing is, I haven't shown it on this slide, have I? I don't think I have. No. we could use this same predicate. We could pass it to standard sort. Standard sort takes an optional predicate, binary predicate, a comparator. So we could, if we wanted to sort the whole array, as the whole vector, which was your original suggestion, we could call standard sort, people.begin, people.end, and compare person. And that same function would then sort the whole array alphabetically. Last name and then first name.
Probably worth mentioning as well that there is stood partial sort, which you can use to do effectively the same as this thing if you wish to make it sort. Move only the first person up.
Yeah.
You've also got like a stable sort, but that includes sorting the rows by size as well as something.
What stable sort does that standard sort doesn't. So the difference is the stable sort doesn't reorder two elements that compare equal. So in this case, I asked you what happens if two people compare equal. Well, with standard sort, it sorts them in order according to your comparator. But let's imagine that we didn't worry about the first name thing, and we only sorted on last name. Well, in that case, we could end up with two people with the same last name being swapped over. Stable sort guarantees that if two things compare equal, they remain in the same order. It means that stable sort is a bit slower than standard sort, and it has to use some extra memory to have these guarantees, but that can be important for some applications. So to very quickly go through this, we saw an implementation of standard counts. Well, there is a corresponding countif. So this time, instead of a value to search for, we're going to use a predicate. And we're going to count how many times this function returns true. So we're writing a template again, involving two types, one called iter and one called pred. And here's our implementation. You see it's very similar to what we had for count earlier. We initialize the counter, we iterate from everything from the first up to but not including the last. But now, in the body of our loop, what do? We've been passed a predicate function. So we call that function and we pass it the value at position first, where first gets updated as we pass through the loop.
You can pass function type name as well. Function type name. So you can use type name for passing functions too.
Yes, you can. Yes. Yeah. So it's going to call whatever function we've been passed, the function called pred. It's going to call that function and call that function with an argument that is star first, the value of the thing at position first. And if that function returns true, then we increase our counter.
So when would it return true?
If the predicate returns true,
when would it return true?
Well, it depends. You can pass any predicate.
Argument.
Sorry?
Does the pred function have an argument?
Yes, so pred, in this case, is required to be a unary predicate.
So
Okay, a function that takes one argument and returns a bool.
So what are you passing to pred?
Why?
No, what are you passing to pred?
Well, let's have an example of a suitable predicate function. Here we've got a function called starts with t, and returns a bool, and it takes a single argument that's a reference to a string. And the implementation of this function is a bit squeezed to get it to fit on one slide. First of all, it checks whether the string is empty. Well, an empty string doesn't begin with t. So it throws that away. And then it looks at character 0 and returns whether the character 0 is equal to a capital T. So now I've got a vector of strings. People. With Tom, Ollie and Tristan. And now here's the magic bits. That I can call this COUNTIF template, function template, up there. And I can call it on our people vector. So it's going to go through every element in our vector. There are only 3 of them, but still. It's going to go through them and say, first of all, it's going to look at Tom. It's going to execute pred with the string containing Tom. So it's going to call starts with T, and it's going to pass it the string Tom. So it's going to say, okay, is the string empty? No, it's not. Is the first character a capital T? Yes, it is. So the predicate is going to return true, so we're going to enter the if statement there, and it's going to increment the counter. And then the next one, it's going to look at Ollie. Okay, is the string empty? No, it's not. Is the first character a capital T? No. Okay, so we skip the body of the if statement, and the loop's not incremented. And then it's going to look at Tristan, same thing again, begins with a capital T. So it's going to increment the counter.
When it comes to people, I don't count.
So this function, hopefully, our COUNTIF here, will return true. Sorry, will return 2. True, 2. Yeah. Because there are 2 people in the list whose names begin with T.
Just to totally make sure, to go over a question that I asked earlier, because you're using a template here, you would call this generic programming.
Yeah, I guess. I really don't get too hung up on the terminology.
Well, no, I've used templates dozens of times, and I just never said that this is generic programming. I just use it more than dozens of times.
Yes.
If the term generic program, I'm responding to the question. Hi.
Sorry, I think you're these.
No, if the term generic programming confuses so much, there's a Wikipedia article on programming paradigms where we see all the different styles with explanation. And maybe that resolves some of the confusion that we have.
Well, no, it's just that sometimes when you're like writing code, you just write code without saying, oh, well, this is what you would call generic programming.
Yeah, absolutely.
You know, like,
And sometimes I'll write code and have somebody else look at it and go, oh, you've used functional programming there.
Yeah, that's what I'm saying. Like when you write in Java, I wouldn't say, oh, yeah, I'm using my functional programming. It's a particular language.
Exactly.
Even though I'm using JavaScript, I wouldn't say I'm using functional programs and passing functional arguments.
Yeah.
As he says, you're right. You don't. You just say, okay, I'll do that.
Exactly. Yeah. Sorry, was there another question at the back? Do you have a hand up? I guess not. So, once again, this is going to create a version of our COUNTIF function, a specialization of COUNTIF, just for dealing with vectors of strings and for our particular comparator. So it's going to be able to inline this comparator, it's going to be able to do things really fast.
You mentioned that, maybe you mentioned it, I missed it, but the function at the top is called count, not count.
Ah, god damn it.
It's going to upload these later, so it's not a fixed.
Yeah, because I will forget to change them otherwise. I don't know why you waited till it had been on the screen for 10 minutes before you told me.
It's a constant prep ref as well.
You don't want to do that.
I'm joking.
What does COUNTIF return? Is it a size T?
A size T, yes. Which is an alias for something that's appropriate for sizes.
Sure.
So
I just wonder why you use auto rather than size T.
Just because it's less typing. Right. So here we're calling our function, our COUNTIF template. We're passing it a function type. C++11 also gave us these swanky lambda functions. So if you're familiar with other languages that have lambdas, you can do that in C++ as well. The syntax is a little bit odd. You use some square brackets to introduce the lambda, and you can put your lambda captures in there as well. We don't have any in this case. And we say that our lambda takes a parameter, deduce type, reference to deduce type, and we say our parameter lambda returns true if the size of the string is less than or equal to 3. So this is a really neat way of not having to define a separate function to use as a predicate when you're calling standard library algorithms. Because it'd be a bit of a drag if we were right in the middle of our body of our for loop. We had to, jump up to some function that's defined up there. So this thing with lambda functions allows us to write it all in one go. So this.
Lambda as a predicate.
Yes, exactly. That's what we're doing here. Yes.
You use the square brackets in the beginning.
That's just the syntax that you have to use.
So you have to use the square brackets.
You have to use the square brackets.
That is weird. Why don't I call numbers?
Because square brackets is less code, less typing. Yeah.
You use a lot of constant type, which I get on a global scope, but within the lambda function, there is no danger of accidentally manipulating the variable.
That's true, but well, how deep do I want to go with this? It's almost, well, it is always better if you're not going to modify anything, put const in there because you never lose. And in fact, would we be okay here? We might have a problem here because when we dereference first, we're going to get a const string reference from it. And so we have to use const auto here, otherwise it's not going to... I don't actually know off the top of my head whether it would work if you took the const out. Right, it's 1 minute past 9. And alas, we've had lots of really good questions, so we have not much time left for our exercise. In fact, we have no time left for our exercise, but luckily, you guys have got a whole week where I'm sure you have nothing else to do, and you really want to do some C++. So, I would very much encourage you to go to that URL, check out the task. It is not easy, I will warn you now. If it's your first time writing templates, well, I've actually written all the boilerplate for you. I've been quite nice. But the idea is to get you to write some of the right implementations of some of the simpler algorithms that are in the standard library. They get progressively more difficult. So if you've understood counts and how that works, you'll probably have no problems. And then, we just added a few little complications, predicates and things like that. Don't worry, I'm not asking you to do standard sort or anything like that. The most complicated is binary transform, I think. Okay, so that's it from me. Thank you, everybody, for coming. Again, apologies for the delayed start. Thank you very, very much to these guys for hosting us. This is a really cool space as well.
Thank you very much,
so,
for...
Thank you, everybody. I hope...
Okay, so ladies and gents, as a tradition, we will be going to a local park. I encourage. Sorry.
I've researched there's 2 nearby.
I encourage you to join us and say thank you to Tristan, Ollie, Justin.